I want to give the floor to Alexander Chernokulsky. He's an employee of the Institute of Atmospheric Physics, the Obukhov Institute of the Russian Academy of Sciences. And he's going to make a presentation on contemporary global and high-latitude climate change. Alexander? Yes, thank you. Thank you very much, Sergey Alexandrovich. Just a second, I'm going to share my screen now. Professor Bartolev asked me to give a popular scientific lecture, and this is something that I have been doing for the past 2 years, although I'm an expert on various natural disasters and climate change. But in the last couple of years, I have been giving a lot of public lectures, and as far as I understand, this school focuses on climate change and other disturbances. So I would like to give you a general idea of what climate change is and how it affects high latitude areas.
My slides will be in English, and I will speak Russian. Буду говорить по-русски. Ну, когда мы говорим об изменениях климата, часто всплывает...
When we talk about climate change, very often we refer to...
Организаторы могут выключить остальных участников звук, там это легко.
Сейчас это за рубежа, но он на русском говорит.
Да, продолжим. Вот есть цель устойчивого развития, и там записано, что мы должны...
So once again, the United Nations identify sustainable development goals, and there is goal 13, climate change, take urgent action to combat climate change and its impacts. Laymen may think, why combat climate change? What do you mean? Climate has always existed, has always been with us, and of course it changes, and why are we supposed to resist the change? Well, and what is climate anyway? Climate is an ensemble of states of the Earth's climatic system: atmosphere, hydrosphere, biosphere, lithosphere, and cryosphere. And one of the systems that we are studying now, the biosphere, is also an important component of the climatic system over a relatively long period of time, say 30 years. That's what we mean when we say climate and when we say climate change. This is a picture that is well known, I believe. This is how temperatures have been changing. If you look at recent years, 2019, 2016, the warmest years, already the temperatures have been 1 degree higher than the 20th century average. But if you look from the beginning of the century, the temperature seems to have grown by 1.5 degrees. There is the polar enhancement component here as well. These are the trends for the period of 76 to 2019. Globally, the temperature was growing by 0.18% every 10 years, all land about 0.3, and in Russia, every 10 years, temperatures grew by 0.5% every year, and in the Russian Arctic, it was even faster, and this is the so-called polar enhancement, 0.7 degrees every 10 years on average. But we see changes everywhere, not just in one particular part of climate or climatic system. For instance, glacier mass is reducing, sea level is rising because of thermal expansion and because more water is generated by glacier melting. Permafrost temperature is also growing everywhere in multi-year permafrost soil, and there have been always other trends recorded, the so-called marine heat waves. The land heat waves is a well-known phenomenon. It was studied in the past, but in Russia in 2010, If you remember that the summer of 2010, in Europe, for the several past years, there have been several land heat waves, but marine heat waves is a relatively new phenomenon, was discovered recently, but we also see that there is a rise in those heat waves. I could be showing you many more of such diagrams and graphs. We can see that those changes are occurring everywhere in the climatic system. And then natural disasters, all kinds of acts of God. And there is this insurance company, Munich Re, and they insure risks, and they publish reports every year. And this is their assessment of various natural loss events. The red ones, geophysical events, you can see that in the past 40 years, there haven't been many changes there in the number. But if you look at meteorological events, or what they call the climatologic events and the hydrological events, we observe a noticeable rise. In the past, there were about 200, 300 events per year. Now we're looking at numbers in the range of 700, 800 natural disasters of a large scale every year. Of course, you cannot argue with those numbers. If you look at the number of natural loss events in Russia, this is a Russian Meteorological Bureau data, Roshydromet data, and this is the number of various hazards that cause significant damage, economic damage, and this is the number of projected events. You can see around the year 2000, the projections were worse. Now they're getting better, but in any way, we see an increase in those numbers to 400, 500, and this is the number of meteorological hazardous events that are recorded in Russia. They may not have resulted in particular damage, but these are all kinds of fog or strong wind, and again, there is a definite rise there. It's just that there is another thing. Roshydromet does not record every single event. Tomorrow, Andrei Shikhov will make a talk, and he will speak about tornadoes. It's an underestimated threat in Russia. I've been studying it in the last year together with my team, and this is an undervalued, underestimated risk in the country. In 2017, for instance, there were 342 tornadoes that passed through the territory of Russia. And in accordance with the official statistics of Roshydromet, there was only one tornado, 1 versus 342, a major difference. Here in orange, you can see the tornadoes identified by observers, and the blue ones are satellite data. Andrei will talk about that tomorrow. Please come and listen to his presentation, because this is something that we have been observing for the past several years. Precipitation. Are there any changes there? Of course. Is this a negative change? Unfortunately, it is. These are Russian trends. Not very big. The total amount of precipitation is growing, but not very much. The problem is the nature of the precipitation changes. The black is the total precipitation. Red is conventional, and blue is marine precipitation. And we can see that in 1970s, large-scale precipitation made the greatest impact. Their share was greater. Now, convection precipitation makes a greater contribution into the total number. And also, there is a redistribution of precipitation over time. It's like a rosebud chain, and this is the number of rainy days during the year. In the past, dry periods and wet days, they were distributed pretty evenly across the month. A day of rain, a couple of days that would be dry, a couple of days of rain, a dry day. But now the picture is different. The number of days is the same, but the duration of those periods, of rainy days and dry periods, it's changing, and those days tend to cluster more, and this is quite dangerous because this is a risk of flooding. And on the other hand, when you have 15 days without rains, there is a high risk of droughts. So if you look at the total for the months, it may be the same value as we have been observing in the last years, but now because of this changes in the structure, the threat is high. And convective clouds, not only convective precipitation is growing, but also or the share of convective precipitation and total precipitation, but there is also convective clouds. Those are Arctic stations, observation points, and this is what we have found out on the Western Arctic. That's data for almost 80 years. We've been monitoring clouds there since 1940s. And this is Eastern Arctic. We have had data for the past 20, 30 years, and we see that, especially in autumn, there is an increase in convective clouds. In the Arctic, the changes are happening very fast, and the climatic changes are occurring extremely energetically. Snow, precipitation, everything. Gareth Marshall will speak after me, and I don't want to cannibalize on his presentation. Vegetation, you are better experts than me. This is a well-known statistic. CO2 increase, an increase of plant primary production, the so-called global greening, the greening of the planet, the NDVI growth. The temperature and precipitation changes also results in changes of the distribution areas for various environmental systems. For instance, there was this 2016 article by Chpakova and others. They're showing how tundra will be shifting towards north, and it will be replacing the forest tundra. Whether the soil will adapt, whether it will be adapting at the right pace, that's a big question mark. And in the south, steppes will be expanding because of fires, wildfires that become stronger in the south. And wind-related disturbances like tornadoes or squalls that Andrei will be talking about. Also, invaders and I mean, there are the insulation, active radiation changes, all of this. I mean, I'm sure that our colleagues will be discussing this in more detail in the subsequent presentations. Now, let's try to understand why researchers, why scientists believe that modern climate change is attributable to human activity. Where is your proof? Well, first we need to understand what has an impact on climate change. What are the factors? We've got external factors, we've got astronomical factors like solar activity or the Earth orbit parameters, or geological factors like volcanic eruptions. And then there are also internal factors. For instance, the climate is a system, it has 5 components, and there are fast components like the upper layer, the atmosphere, and then there are slow components like the lithosphere and the bottom of the sea, the bed of the sea. And in the slower shells, those shells, it's also an internal factors. What is the difference between external and internal factors? The climate does not affect the sun. The sun can affect us, but our climate has nothing to do with the sun and solar activity. But the climate can have an impact on internal factors. And also humans. It's a big question whether humans should be considered an internal or an external factor. I think it was an external factor originally, and it was like the sun. The climate, well, the humans didn't affect the climate very much. In the past, they logged forests, but to a known extent. But now we have many more resources to affect the climate. Now we are becoming an internal driver for climate change. Now, the astronomical factors, the Milankovitch cycles, the eccentricity of the orbit, it's an ellipsis, it's not round, it's not circular, and there are fluctuations in the orbit, and there is a precession of the orbit if you either rotates, and also the tilt of the axis for 40,000 years. And all these superpositions of these fluctuations, they redistribute the energy basically. And in the summer, in Northern Hemisphere, we may be seeing more or less energy because we are not an aqua planet, I mean the Earth. Therefore, feedback is initiated, less energy, more snow, more albedo, more snow, and that's why we have these transfers between ice ages. So we are either in an ice age or between ice ages. Right now, this vertical line, this is where we are. This is where the eccentricities, this is where obliquities and precession, they are straight lines. We do not see any changes there. And to explain our current trends, just by referring to Milankovitch cycles, is just not feasible. And then solar activity, we know that solar is active and there are different cycles. Again, in solar energy, the 11th year cycle or 11-year cycle is the best known one. You can see here how solar activity changed over the past 4 centuries. Here, the problem, well, it's not a problem. You have to understand that this change in solar activity is roughly 1 watt per square meter, so perpendicular surface. But if you consider that the Earth is a sphere, you divide it by 4, you acquire the albedo, and you see that for the Earth's surface, the solar activity is about 0.2 watt per square meter, while human activity induces 2 or 3 watts per square meter on the circular spheric Earth surface. So we're talking about a tenfold bigger impact. Geological factors, volcanoes. Volcanoes have always been a major source of the atmospheric content, CO2 evaporation, greenhouse gas effects. At the moment, volcanoes are pretty weak, and the CO2 flux from volcanoes is 300 million tons a year, while anthropogenic activity produces 35 billion tons of CO2 a year. And often in Russian press, you read that an eruption of one volcano can do more damage than humans in a decade. Well, it's not true. One of the strongest eruption in the last several decades, the Pinatubo eruption, it ejected 42 million tons of CO2, while in 1991, anthropogenic activity accounted for 23 billion. Again, we are talking multifold difference. And volcanoes for 2 or 3 years can make the climate cooler if the eruption happens in subtropical areas. And the volcanoes can also have an impact on vegetation in the tropical areas, even if in the tropical areas there is eruption, and the plume goes into the stratosphere. There is the so-called Brill-Dobson circulation. The ash will be distributed in the stratosphere for 2 or 3 weeks, and there the sedimentation takes a while. It takes 2 or 3 years. It happens slowly, so that's why for 2 or 3 years we see some cooling down effect following eruption in 2016. Remember the summer without yellow, the Tambora volcano, Lord Byron was in Switzerland, and he was writing his poems, and Mary Shelley wrote Frankenstein during this cold period caused by the eruption of the Tambora volcano. Internal variability, El Nino, the Pacific, then stratospheric fluctuations. So superposition of these cycles can accelerate or decelerate a trend. You can look at the early 20th century, the 10-year Pacific oscillation and the Atlantic oscillations. You superimpose these cycles, and you see that this oceanic cyclicity led to a deceleration of warming. But these superpositions alone cannot explain climate change well enough. Human-caused changes. People have always been logging forests. Of course, this leads to changes in reflectance. We know that in a forest, it is lower than on agricultural land. So if you look at this reflectance soil or surface albedo per square meter, and this is how humans changed the surface albedo. Aerosols, suspended particles, when we burn fossil fuel or coal, there is a lot of CO2 emitted into the atmosphere, and our British colleagues know, they know very well that because of coal burning in the fire places of London, there was the great smoke in 1958, which caused a lot of deaths in London, and laws on clean air were adopted. And aerosol emissions, they peaked in the 1950s, and then they started to go down. Aerosols tend to chill the atmosphere. When you add the aerosols to the atmosphere, they produce a cooling effect. They do not reflect solar light, and indirectly they enter into contact with clouds. They make clouds brighter and longer lived. So basically this also leads to a cooling. Between 1950s and 1980s, greenhouse gas emissions and aerosols, they offset each other. But starting from 1980s, when aerosol emissions went noticeably down, this compensatory effect of the aerosols, it disappeared, and that's why global warming accelerated. Now, biggest human impact on climate, greenhouse gases, the emissions are still growing. Today, about 10 billion tons of carbon are emitted. Sometimes you read 35 billion tons, but 35 billion tons stands for CO2, while 10 billion tons is the tons of carbon. And 1 billion ton is 1 gigaton of 1 petagram. And we continue to intensify the greenhouse effect. We amplify, of course, there were greenhouse gas effects even before humans. Without greenhouse effect, the average temperature on Earth is not -18, but +15 Celsius. So it's because of greenhouse effects, we have water in 3 different aggregate states. Yes.
Да, ну попробую говорить, но это, конечно, тяжело, когда кто-то еще.
I will try to speak, but it's extremely difficult to talk when other people are interfering. Anyway, so the greenhouse effect, the temperatures in lower strata of the atmosphere is growing because there are greenhouse gases in the atmosphere. They're transparent to short waves, and they are opaque for long waves. They absorb long waves and they re-emit them back. And our main greenhouse gases are water vapor. That's about 2/3 of all GHG. CO2 is just a quarter of greenhouse gases effects, and the rest jointly produce 9%. Water vapor, although it's the main greenhouse gas, it has a very short life, while carbon dioxide has a long life. The relaxation time, the concentration time. If you increase the concentration of CO2, it will stay high for a long time because the chains, the exchange processes between different components of the climatic system will not speed up the reduction in concentrations, will prevent fast reduction in concentration. Warming attribution, well, first of all, unprecedented rise in CO2. These are observations since 1958, the Mauna Loa data. You can see here the data. And if you look at ice cores, in the last 8,000 years, the concentrations were changing within a particular range, but now at the end of this plot, you can see a vertical line going up. Albert Gore, to demonstrate this, had to hire a fire escape or a crane that lifted him all the way into the sky. So these are the, well, we know that humans produce about 5 or 6% compared to plants and oceans, but this is not balanced. There is more CO2 runoff into the ocean and into the vegetation, but still 4 gigatons of CO2 remains in the atmosphere every year. This is the atmosphere, this is what goes into the land, and this is what's sequestered by oceans. The concentration of CO2 in the atmosphere continues to build up. Then there is another evidence to warming attribution to humans. So of course, we see that there are CO2 emissions and everything else, but maybe we are missing something out. But isotope composition, the fingerprints, really is the best evidence ever. Suess discovered this effect for the first time in the 1950s. He suggested looking at C14 isotope and its reduction would be attributed to a new source of C14, of CO2. C14 is radioactive. And of course, in coal and oil, there is none of it yet. It has already decayed. But when you when we started nuclear testing, there is no more C14, or rather, there is. It doesn't make any sense anymore to look just at C14, but C12 came to substitute C14, and the reduction, this decline of C13, the C12. It tells us that there is a source in plants. It's either plants respire, their respiration is greater, or it's because we are burning coal. We do not have any evidence to say that plants' respiration changed from the 19th or 20th century, but there is no other explanation but human activity. And recently we've been also monitoring CO2. This is an article from Nature in 2015. They measured the incoming radiation effect of CO2 per square meter. This is forcing, and it's growing, and it correlates very well with what we are measuring in the atmosphere. And there is another article, there is this growth. I mean, this body of evidence is good proof. Ocean acidification is trying to absorb all the CO2, it becomes more acid. This is the mesopause between the stratosphere and atmosphere, and stratosphere, mesosphere. We've been observing this area since 1950s, and there is an intensification of the greenhouse effect in those areas. And then there is heat accumulation. There are other drivers of climatic change and variability. And then there are also models which can be used as evidence. Modern climatic models cannot reproduce contemporary climate change if they do not take into account anthropogenic forcing. This is natural variability, the red line, and if you account for natural and anthropogenic forcing, the model reproduces the actual climate change with a high degree of accuracy. Again, we can always look at the 1970s or 1980s models. How well do they reflect or predict global change? Over here, you can see the Boudicca projection and Hansen projection, 3 different scenarios, A, B, and C, depending on the fossil fuel combustion. And black is temperature. So basically, yes, they are reproducing. Of course, year-to-year dynamic cannot be reproduced in the model because the oceanic variability phases, they will not be reproducible, but the trend is reproducible to a high degree of accuracy. Or take this picture, it's also well known, Hansen, Lensen, one of the skeptics, and this is how he predicted the temperatures would be changing in early 80s. I will not perhaps dwell too long on the implications of climate change. We have our own nightmares anyway. You can read the IPCC report to, get more horror stories. They expect sea level rise, they expect the increase in storm surges, temperature warming. We expect a redistribution of precipitation. Dry places will become even drier, humid even more humid. There is also melting of permafrost and of the sea ice. There is an increase in acidity of the ocean and an increase in the intensity and frequency of extreme weather conditions. And all of this can lead to negative consequences for biodiversity, for the society, for the economy, for every person on the planet. So we should be trying to mitigate those risks, and at the same time, we should develop strategies for adaptation. Both industries need such strategies, and humans need an adaptation strategy. One of the objectives is to raise awareness and to outreach to the communities. This is something that I've been doing in the last several years. How do you talk to the public? How do you explain people that climate is changing? What are the right words? What words have you to find? Do you have to find to explain this to an outsider, basically? There was this a publication in 2011, the countries, and when these countries will actually observe, we will be able to feel the climate change. It's very difficult to explain climate change to anyone in Russia. For that reason, if there are big differences between seasons in your country, then small climate changes may not be noticeable. In equatorial countries, people can feel it themselves, that the climate has changed. It's no longer a climate to which they're used. But in Russia, people don't feel it, they don't see it, they can't experience it. This is a good illustration. I mean, this person is walking a dog, and the dog runs everywhere, to the right, to the left. You see changes in weather, but not in climate. And in order to understand the climate change, you need to look back and look at the traces left by the dog, really. But laymen, they don't do it. They're not used to working with scientific data, analyzing this data, referring to scientific data all the time. There is this project towards the COP26, Sperare. It's a project aiming to facilitate dialogue between the academic community and the public. On the 16th of October, we held a roundtable discussion on how to promote knowledge about climate and how to educate population about climate change. We invited journalists and psychologists because this is an interesting and a difficult topic. How do you explain things to people but not scare them and tell them how they should adjust their behavior? In December, we're planning to hold a British-Russian panel discussion. We'll see. I don't know, maybe whether the COVID-19 pandemic can be considered a proxy to assess the society response to a major threat, because climate change is also a major threat. COVID-19 is one of is a one-off, a very immediate change, but climate change it has delayed consequences. And we are going to do a poll and publish the results of a social poll together with Levada Center on Society Awareness of Climate Change and Adaptation Strategies. I think I should stop here, and maybe you will have questions that I will be very happy to take. Thank you very much, Alexander. This is the presentation that I was hoping very much that you would deliver. I wanted people to hear exactly what you have just presented. Although we hear a lot about climate change, we all have a general idea of climate change, but there are some things that are natural and obvious for a climatologist, while for me, they are novel and exciting. Thank you very much. Do you have any questions to Alexander? Please go ahead. Yes, sure.
Вам не кажется, что за счет генерализации вы выплеснули вместе с водой и ребенка?
Do you believe that you are throwing the baby away together with water because of your generalization? Because you've been demonstrating annual trends of temperature change in the Northern Hemisphere, while in the Southern Hemisphere, for that hemisphere, we did not see any data. And also, if you would be reviewing data for summers and winters, you will see that in summer, there are virtually no changes. All the changes are occurring in winter.
Генезис изменения кроется в другом.
And the genesis of this change is different. It's the volcanoes at the Gakel range. Methane is released. Okay, can you state your question, please? Briefly, thank you. Well, unfortunately, the speaker did not provide separate trends for winter and for summer. Well, of course, we have trends for summer and for winter, and everywhere they are positive. And in the Southern Hemisphere, it is a global process. And of course, in some season, the trends are more pronounced than in another season, depending on the region. But temperatures are growing throughout the year, be it spring or summer or autumn or winter. As to volcanoes, I showed you the numbers. The eruptions of volcanoes produce 3 times less emissions than humans. I simply cannot agree with you. And of course, we don't have enough time to show all possible data. The trends, really, they don't matter. Trends are just an indicator. If there are no questions from the room, then we have several comments left in the chat. Let me read them. We received several thank yous. Thank you very much. It's a good compilation, well-presented information. CMIP6 data, when is it going to become available? Yes, but Ilya has already sent an answer that we already have the data, and yes, they are already available. Okay, thank you. There is another comment in English. Thank you very much, Alexander, for a very detailed and useful presentation. There is also a question, where do we find the data? Where can we find them? But I see people already sharing links in the chat. That's nice. So, no, we don't really have any questions on the chat, as it turns out, just the comments. Are there any other questions? Alexander, thank you very much. Truly, that was rather educational. Since this is a school for young scientists, this is exactly the lecture that we were hoping to get. Thank you very much.